Welcome to CubeWorks. 6 weeks before a 132-kilowatt motor on a primary production line was about to seize, an event that would have destroyed the motor windings, bent the shaft, and forced 22 hours of emergency repair time, a sensor detected something. Look at this line graph tracking motor vibration. The baseline frequency was holding completely flat. Then, specifically at 6.3 kilohertz, the bearing frequency amplitude spiked 140% above its 30-day baseline. The sensor that caught this anomaly had been mounted on the motor for 4 months. It cost 4,500 pesos. By triggering an early intervention, it prevented an emergency repair that would have cost 620,000 pesos in parts, labor, and production losses. Catching a fault like this is not a matter of luck. It is a matter of physics. Bearings fail in a strict, predictable sequence. Your motor announces its structural failure weeks before it happens, if you are listening. Most modern manufacturing facilities operate with a massive vulnerability. They run hundreds of motors, pumps, fans, and gearboxes with no condition monitoring whatsoever. Every single one of those mechanical components is governed by inevitable physical degradation. Every bearing has a finite limit. Every shaft will develop misalignment. Couplings degrade over time, and gearbox teeth accumulate surface fatigue. Without active monitoring, these developing failures remain invisible. If you rely on human senses, waiting until a machine stops running, trips a thermal overload, or starts making an unusual grinding noise, the internal damage is already severe. Catching a bearing failure at stage 1, using early vibration signatures, requires a repair costing between 3,000 and 8,000 pesos. Waiting until stage 4, a full mechanical breakdown, pushes that repair cost up to between 50,000 and 500,000 pesos, depending on the collateral damage caused when the machine tears itself apart. For most industrial motors, the chronological gap between a stage 1 microcrack and a stage 4 catastrophic breakdown is exactly 4 to 12 weeks. Vibration analysis is the most technically mature methodology designed to cover the specific gap. We are not talking about proprietary black box algorithms. These diagnostics are governed by established international standards, specifically ISO 10816 and ISO 20816. That 4 to 12-week gap is the literal definition of your predictive maintenance window. It is the strict timeframe in which reliability teams must operate to avoid unplanned downtime. The entire premise of vibration monitoring relies on one established rule of physics. Bearing failure is not random. It follows a consistent 4-stage progression. This chart maps that mechanical degradation over time. Stage 1 is the ultrasonic signature. Subsurface fatigue begins deep inside the bearing material. It is completely invisible to the naked eye and inaudible without ultrasonic instruments in the 50 to 300 kilohertz range. This occurs weeks to months prior to total failure. As microcracks develop in the bearing races or rolling elements, the progression enters stage 2. These cracks generate distinctive defect frequencies in the 500 Hz to 20 kHz range. This 2 to 10-week window before failure is your primary detection zone. By stage 3, those microcracks propagate and surface spalling begins. The curve steepens, broadband vibration elevates significantly, and the friction sometimes becomes audible to trained personnel. You now have days, perhaps 2 weeks, left. Finally, the curve plummets to 0 at stage 4. This is catastrophic failure. The bearing cage collapses, rolling elements dislodge, and the shaft deflects. Time to failure is exactly 0. The math dictates your strategy. Operating within the stage 2 window gives you a time frame perfectly wide enough to schedule a planned shutdown and source parts, while keeping you safely away from the catastrophic collateral damage of stage 4. You cannot capture a stage 2 defect frequency with just any hardware. Industrial IoT monitoring requires MEMS accelerometers, which measure precise vibration acceleration and typically cost between 3,000 and 8,000 pesos per sensor. For basic monitoring on standard motors and pumps, the sensor must meet strict minimum technical specifications. It needs at least 2-axis measurement, a frequency range capable of reaching 10 kHz, and a sampling rate of at least 1 kHz. Where you place that hardware is just as critical as the hardware itself. For horizontal motors up to 100 kilowatts, place an axial sensor on the non-drive end and a radial sensor on the drive end. They must be mounted directly to the bearing housing, nowhere else. The geometry changes slightly for different assets. For pumps, place the radial sensor on the pump bearing housing and the axial sensor on the coupling side. For fans, you need radial measurements on both bearing housings and axial on just one end. Mounting methodology also dictates accuracy. An adhesive pad is acceptable for a temporary initial survey, but the material degrades and alters the signal. For permanent monitoring, stud-mounted sensors provide the rigid connection required for reliable frequency response. If you select a sensor with inadequate sampling rates, place it on the motor frame instead of the housing, or use weak adhesive, you will record corrupted data. Corrupted data cannot predict a stage 2 failure. Once the hardware is correctly mounted, the vibration data it collects is analyzed at 2 distinct levels: overall vibration level and frequency spectrum. This table breaks down overall vibration. Measured as RMS velocity in millimeters per second, it provides a single number representing total vibration energy. The ISO 10816 standard categorizes this into severity zones: Zone A for new machines, down through Zone D, indicating dangerous operational limits. For example, on a standard 15 kilowatt motor, an overall reading of 2.1 millimeters per second falls squarely in the healthy zone. If that reading climbs to 5.8 millimeters per second, you have crossed a severity threshold and require immediate investigation. But overall vibration has a strict functional limit. It can tell you that mechanical friction has elevated, but it cannot tell you which internal component is causing that friction. To diagnose the specific fault, we use this fast Fourier transform, or FFT, spectrum diagram. The FFT breaks down the complex raw vibration signal into individual frequency peaks. Because every mechanical component possesses physical dimensions, its faults generate predictable mathematical frequencies. We map an inner race defect to the BPFI peak. An outer race defect maps to BPFO. A rolling element defect maps to BSF. And general shaft misalignment presents clearly at 1 times or 2 times shaft speed. By combining the bearing's physical dimensions, the shaft speed, and the FFT spectrum, engineers can mathematically isolate a microscopic outer race defect weeks before the degrading metal ever makes a sound. This architectural flowchart illustrates how that diagnostic data flows from the machine floor to facility management. The stack routes data from the MEMS accelerometers, pushes it through an MQTT broker, and delivers it into a centralized IIoT platform holding the trend dashboards and alarm engines. For critical assets, continuous high-frequency sensors operate on a strict operational cadence. They publish root mean square values every 10 to 60 seconds for continuous trending, while allowing operators to pull raw waveforms on demand for deep spectral analysis. Conversely, for non-critical machines, a lower-cost approach is to route standard analog sensors into an existing gateway. This provides overall RMS trending to catch late-stage failures, but it intentionally sacrifices early spectral detection to save on hardware costs. Regardless of the hardware, alarming requires a strict dual-threshold configuration. The alert threshold triggers at 30% above the 90-day baseline. The warning threshold triggers at the ISO Zone C boundary. The critical threshold triggers at Zone D, or 100% above the baseline. These thresholds map directly to escalating facility responses. An alert generates an automated maintenance notification. A warning generates an active work order. A critical breach triggers an immediate operational review, and likely a machine shutdown. The logic here relies on the rate of change. If a motor reads 2.1 millimeters per second today and climbs to 3.2 millimeters over 90 days, it hasn't technically breached the absolute ISO threshold, but that is a 52% increase in friction. That mathematical velocity alone will generate an alert. Absolute vibration values tell you how much damage exists right now. They are lagging indicators. The trend rates tell you how fast the machine is destroying itself. They are your leading indicators of future failure. You cannot immediately blanket every rotating machine in a facility with sensors. It is financially and operationally inefficient. You must prioritize using a criticality matrix, scoring each asset on 2 distinct axes. The first axis is the consequence of failure. This is calculated by taking the production loss per hour, multiplying it by typical downtime duration, and adding the hard cost of physical repair. The second axis is the probability of failure. This requires assessing the machine's age, its operational duty cycle, the harshness of its environment, and its historical maintenance records. When you run these calculations in a heavy manufacturing environment, specific assets universally fall into the highest priority quadrant. These are your primary production line drive motors, main cooling tower fans, and primary chiller compressors. Before committing budget to permanent sensors, execute a manual vibration survey. Have a technician use a handheld diagnostic meter to measure the overall vibration on every critical motor across a single production shift. This establishes exact rules for hardware deployment. Any machine that measures above ISO Zone B or shows an upward trend from Zone A to Zone B over 30 days gets upgraded to permanent IIoT monitoring immediately. A 2-day manual survey requires minimal labor and a 15,000 peso handheld instrument. It is an insignificant expense compared to the financial risk of deploying tens of thousands of pesos worth of permanent sensors on stable, low-priority assets. Deploying predictive maintenance is a targeted business strategy governed by financial risk matrices. You are leveraging the physics of defect frequencies to protect the economics of your production schedule. In heavy industry, the element of surprise is the single most expensive variable a facility manager will ever face. By aligning high-frequency diagnostic hardware with mathematically predictable defect physics, you eliminate that surprise. You buy back the time required to control your own maintenance schedules. Listen to the data, find the anomalies, and close your predictive maintenance window before a failing bearing becomes a catastrophic shutdown. To learn more about implementing predictive vibration monitoring in your facility, visit CubeWorks today.